Thanks everyone for coming. And yeah, today we're very excited to have Rohan with us, who's a final year computer science PhD student at Stanford, advised by Alex Aiken and Fred Kjolstad. He's also a part-time researcher at NVIDIA. He's generally interested in programming languages and computer systems, with a focus in systems for parallel and accelerated computing. His work has been adopted by projects such as Legate, a runtime system for distributed scientific computing. And he's also received numerous awards, including the NSF Graduate Fellowship, the NVIDIA Graduate Fellowship, and several publications in top conferences, including PLDI, ASPLOS, SC, among others. So yeah, please join me in welcoming him today to talk to us about productively programming accelerated computing systems.
Yeah. Thanks, extended introduction. That's usually a much more embellished bio than I would usually say about myself. But yes, I'm a PhD student at Stanford. I work with Alex Aiken and Fred Kjolstad. And I thank you guys for inviting me to speak today. I'll be talking about my work, which is focused on making it easier to program high-performance accelerated machines. So a large variety of accelerated computing systems are being built, including individual accelerators, like modern GPUs, single nodes containing multiple accelerators, up to large-scale modern supercomputers, which contain hundreds of thousands of interconnected accelerators, all of them need to be programmed as a single system. We really care about programming these machines because I think that they are at the forefront of tools that we as humanity have to tackle critical challenges and understanding the world around us. This means running important workloads like in computational science, so physics, biology, chemistry, climate science, the ever-important workload of machine learning and artificial intelligence, as well as large-scale data analytics to understand the amount of data that we as society produce. And so over time, these machines are becoming increasingly powerful, meaning they offer more and more flops, more memory capacity and bandwidth, meaning that we can run larger versions of these applications we care about. We can run higher resolution simulations, and we can run them faster than ever before. However, I think in the last 10 years, these improvements have really stopped coming for free, where as these machines offer more performance, they're also becoming more complex to program, meaning it requires us to write new code, develop new optimizations to actually unlock the performance that these machines give. We can't just write the same code and have it go twice as fast as the next architecture. This complexity is arising at all layers of the stack, from individual accelerators up to their aggregation as a distributed machine. When you look at individual accelerators, they're becoming more heterogeneous and specialized. An older generation accelerator, like the Volta GPU, looked like a relatively homogeneous set of functional units to perform different computations within an application, while modern accelerators, like a Blackwell GPU, contains large fixed function units that dominate chip area, like this Tensor Core or Tensor Memory Accelerator, and are used for specific computations, like batch matrix multiplication or tile data movement. This increasing specialization and a desire for performance is causing the relatively stable boundary between software and hardware that we've relied on for many years to start to break down and remove some of that generality, which is often costly in energy and area for us. And the result of this blurring boundary means that many things hardware used to do for us for free for the software, such as having a stable ISA or putting some synchronization of instructions down in the hardware, is now being forced to be done by the software, which is making it harder to achieve high performance and harder to port these machines into the future. Then we look at distributed machines. We're taking these individually complex processors and aggregating them into large, complex hierarchical machines themselves, where a modern supercomputer has multiple nodes. Each node is a hierarchical machine in itself, containing maybe a multi-core CPU, and then multiple accelerators attached, like multiple GPUs. And these accelerators are connected by hierarchical networks where you have fast internode communication, slightly slower communication across racks. And there are many similar challenges, similar and different challenges you would see when programming these machines, such as how do programmers actually talk about distributing their data and their compute across this machine? How do programmers orchestrate data movement through this hierarchical network, using the right communication links for different pieces and overlapping their communication and compute whenever possible? And finally, they need to actually synchronize different subsets of this machine to actually maintain application correctness. So when you look at programming these machines, it's really a full stack problem, where you need to have software all from down the individual kernels that run across your processors and run in high efficiency. And then you need to go up the stack to build layers on top of this that efficiently orchestrate your computations across these distributed machines. And when you combine these kind of challenges, you really end up with systems where programming these is really living at the edge of our cognitive abilities. And it's very difficult to achieve high performance here. And so I have worked on problems across the stack to achieve a vision of productive accelerated programming and have developed technologies to allow us to write high-level composable libraries that target these complex machines and then to port these applications into the future with minimal effort. Concretely, in my PhD, I've worked at all layers here, where I've built high-level composable distributed libraries that present programmers with simple interfaces like standard NumPy and SciPy, but automatically scale to distributed machines and compose with each other, just like they did on a sequential machine. Then below that, I've worked on a variety of distributed runtime system technology to actually support these high-level libraries and contain some of the key programming languages ideas and having these libraries compose both efficiently and correctly. And then at the bottom of the stack, I've worked on systems to actually, for performance engineers, to build high-performance kernels that run across these machines, including systems that allow us to write kernels across this entire cluster, as well as targeting the challenges of working on an individual accelerator. So in this talk, I'm going to talk about just a subset of these pieces of work. And in particular, I'm going to tell you a story about how I've worked to tackle this problem of productively programming these machines. And I'm going to talk at a high level about two projects first, Distal and Leagate, to set the stage for the two separate problems that I'm going to focus on and take a deep dive on later in the talk. And these are going to be the same topics I emphasized earlier, focusing on efficient orchestration of our distributed computations, and then building high-performance kernels that run on these machines. OK. So the first piece of work that I did in my PhD was tackling this problem of writing dense and sparse tensor algebra kernels and running these across an entire cluster, which has applications in both machine learning and scientific workloads. The first project I did in my PhD was building this Distal compiler, which presented a high-level programming language and associated compilation infrastructure to develop these kinds of distributed tensor algebra computations. The key idea of Distal was to separate the descriptions of how we actually break up the computation and break up the data across a distributed machine and factor these into two separate high-level languages that then the compiler is going to mash together and output code that runs well on this machine. This ended up being a pretty neat idea, and the separation of data and compute distribution was actually expressive enough for us to write down a long history of distributed matrix multiply algorithms, from Cannon's algorithm in 1969 to modern communication avoiding algorithms, all in a very compact piece of code, compared to the kind of low-level communication-filled code you might see these algorithms normally described in. We then showed that we could generate tuned, high-performance code from these specifications, being the first system of its kind to achieve performance competitive with hand-tuned code. This plot shows each of those implementations in the previous slide generated and ran on a multi-GPU system where we can achieve performance competitive at 1024 GPUs with this expert-tuned baseline. Then, because we had a compiler, this flexibility enabled us to achieve high performance even for kernels that hadn't been tuned by humans yet, such as this larger tensor contraction. My work on Distal led me to get connected to some researchers at NVIDIA who had built a distributed NumPy library for dense array programming. So they could take NumPy programs and run them across a distributed machine. And they wanted to build a sparse library to go along with this, so you could have distributed, dense, and sparse array programming in the same system. And the key idea, which we went and did, was to use Distal to generate all of these distributed sparse matrix kernels that such a library would need. Because there's so many different sparse matrix formats, kernels, and kind of backends you want to run them on, a compiler dramatically accelerated the process of building this. Once I generated these implementations, though, we realized that there are actually kind of deeper problems about how we put these libraries together in a sane way and how to build independent distributed libraries that actually compose together while achieving high performance. And this is a very different problem than writing individual high-performance kernels. So we've made significant progress on this front, where we've built an ecosystem of distributed libraries called the Leagate ecosystem, which looks just like standard collection-based Python libraries, but automatically scales to distributed and accelerated machines. I've shown some code with Leagate here, where instead of importing NumPy and SciPy, you import our libraries CuPyNumeric and Leagate sparse, and then write the rest of your code in a normal way, a standard conjugate gradient solve. And this code is going to scale from a single GPU to 192 GPUs and achieves performance competitive with these low-level hand-tuned systems like the PETSc library for distributed sparse linear algebra. A really important component here is the composability, where I can take distributed data produced by one library, kind of throw it into another distributed library, produces some more data, which is then passed back into CuPyNumeric, and it all just kind of works without the programmer doing anything, and it still achieves competitive performance with these systems. And since then, engineers in NVIDIA have gone and actually built a large number of libraries in similar ways and actually started building this ecosystem of libraries that programmers can actually put together and just write normal Python code, but scale up as we go. So to enable this composition without actually paying the standard costs of composition, myself and others have developed a variety of analyses that dynamically analyze the computations launched by these independent libraries and weaves them together with just-in-time specialization strategies to match what a high-performance hand-tuned implementation of the same program would do. These analyses include co-partitioning distributed data across libraries, fusing dependent computations and generating specialized kernels, as well as then discovering the kind of data dependencies and data movement required across these library boundaries. And so once you make the right decisions about how this particular software should be composed, getting good performance requires doing this orchestration and analysis efficiently so that we don't lose more from this analysis than we actually gain from the performance benefits. And then we actually need these kernels themselves to be very efficient, that run inside of our libraries and actually run on the individual processors. And so these are the two topics that I'm going to go on in depth today. And in particular, for the first deep dive of this talk, I want to focus on the efficient orchestration of these dynamic analyses to enable these kinds of composable high-level libraries. I've developed a few of these techniques, and I'm going to tell you about just one of them, which focuses on the efficiency of programming systems at this lowest level of the distributed software stack, which actually coordinates the physical execution of computations and data movement across this machine. So for orchestrating these kinds of parallel computations on our high-performance machines, there have been two main families of programming models to achieve this that serve as this lowest level programming substrate. The first one, which I've kind of hinted to already, is the task-based programming family of programming models. So task-based programming models expose a very declarative interface, and they're organized as a large collection of short-lived, atomic, user-defined functions called tasks, and they're connected by dependence edges that correspond to communication and synchronization. And so usually, task-based programming systems have a declarative way of describing what these dependencies are, and then the system is responsible for executing the program satisfying these dependencies. And there's a long history of programming models that implement this kind of task-based model, as well as higher-level systems, like the ones I showed you, that actually correspond to writing down programs and generate programs in this flavor. The second family of programming models here is the actor-based family of programming models, which have a much more operational structure. Actor-based programming models instead are structured as a group of long-lived actor objects which communicate through message passing. So actors get to send messages to each other, and the main way programmers control what's happening here is by implementing a message handler, which says what should this actor actually do when it gets a particular message. And these actors can send more messages. When they get messages, they can run some application computation, or they can update some arbitrary internal state. And again, there's a long history of programming models that implement the actor-based system. And I think that many of these are the models you might reach for if you think that you want to implement kind of a bare metal high-performance implementation like MPI or Charm++. And so to compare and contrast these models and kind of get what I want to talk to, I want to implement the same parallel program in both models. And this parallel program is going to be described by the simple DAG of computations here, F1 through F4, where some of these computations are going to be said to be run on CPU 0 and some on CPU 1. And so this is a pretty simple program, but we'll already see that many of the challenges I want to talk about will be exhibited by this small program. And so in task-based programming models, these graphs are built usually by the target application or high-level system dynamically. So as the application is running, we're going to be constructing this graph. But in actor-based programs, usually they're structured around a statically defined graph. It's usually coming from the structure of a simulation we have in our heads or a neural network architecture where we kind of know what computations are going to depend on each other statically. And we'll see how both of these appear in these implementations. So in the task-based model, it's quite straightforward, given the declarative nature of these systems. A simple model for pedagogy is going to expose the ability to launch computations onto the target processor. And this launch operation is going to return an event, which represents when this particular launch task is complete. I can chain these together in a declarative way by launching another task that depends on E1, which constrains the execution of F2 until E1 is done. And I can kind of chain these all together to implement my larger program. And I've done this in a kind of very declarative way. And so this DAG is constructed as we run the program, and kind of each time we launch task, the programming system sees a new dependency and constrains this execution. And so task-based programming models have some really nice properties. One of them is around composability, where it's very easy for me to see how I would embed this program into a larger program just by connecting the dependence edges inside and out. And the runtime and the system that implements it is going to be responsible for executing these things when they're ready. It also has this property that can make very local changes. So it's easy for me to see how I would maybe move a task on a different processor or add another dependence edge here by just modifying a small piece of this program. The main cost of task-based programming systems is that they have overheads. And since these graphs are dynamically specified, these programming models are usually implemented with runtime systems that interpret these task graphs like one task at a time and must dynamically schedule and realize these dependencies as they appear. As a result, this is going to mean that we spend time actually inside this runtime system coordinating our tasks rather than doing the application work F1 through F4, which is what we really want to get done. And we'll talk a bit more about this later. So if I want to now do this in the actor-based programming model, the main primitives I have are the ability to define new actors and for them to send messages to each other. So in a high-performance, statically specified construction of this program, what we're going to do is we're going to create an actor per processor in our system and group up this DAG for the pieces that each actor or processor is supposed to run. And naturally, there are dependencies here that cross between these boundaries, so our actor is going to need to send messages to each other. And we're going to control this by implementing this message handler, saying what should these actors actually do when they get messages. If I implement this, I'm going to get this following code, which kind of branches on a particular message and then does some work. We can look at what this actually does. So I'm going to kick off my computation by sending CPU 0 a message to begin, which will start running F1. And then once F1's done, we're going to send messages to the other actor and ourselves to start follow-up computations. And then these follow-up computations begin. We're going to then complete that, send another message. We'll run F3, send another message. And then finally, we've executed all the computations in this graph. And so efficient actor programs are often structured as state machines that navigate a state space where they're receiving messages, changing what messages they're waiting for, to then maybe run application computations. And these state machines, these state spaces can have branches in them corresponding to the different orders that these parallel computations may complete in. So that may change which order in which our messages actually arrive. So the actor model has a very processor-centric approach, allowing for the minimum number of messages to be sent and simple synchronization structures that give us really high performance. However, the burden of this performance optimization is often pushed onto the user who has to build these state machines and write this kind of complex code. And it's kind of hard to imagine how I would embed this program into a bigger program. Or if I change a piece of it and want to move a task somewhere else, it would kind of ripple through and affect a lot of these other state cases and result in some non-local changes to the program. And so I view tasks and actor program models as living on this Pareto frontier, where task-based program models give you some really nice programmability properties, but come at the cost of overheads, which can affect their absolute performance and scaling behavior. But then actor-based program models give you very high performance, but come at the cost of some programmability challenges here. So in our work, we actually show that it doesn't have to be this way. And we can define a new Pareto frontier here. We can get many of the benefits of task-based program models, but retain the performance of these actor-based systems. And to do so, I think we show that there's actually a deep connection between these seemingly disparate actor and task-based models. In particular, we show that they're duals of each other, meaning that I can translate between the two models. So I can take an actor-based program and turn it into a task-based program, and vice versa. But more interestingly, this translation can actually be efficient. So I'm not just doing a bad translation. I'm actually going to take my task-based program and get out an actor-based program that runs as well as if the expert had implemented that program from scratch. And this work is inspired by ideas around concurrency management in the operating systems community, talking about how concurrent threads should talk to each other. So I'm going to talk just about this translation from task-based programs into actor-based programs. I want to first say that the way this is done today, right, task-based programming systems are actually already implemented with actor-based programs, but they're implemented as kind of a runtime system. So as our task-based program is running here, it's going to issue tasks that go into, say, a scheduler actor, which is going to maintain metadata about what tasks have been run. And then when they're ready, we'll send messages to workers that actually run the tasks, and they'll send messages back to the scheduler that things are done. And you can clearly see that there's way more messages and coordination that has to occur for any particular computation to run compared to our efficient actor code. And so the key idea of our work for this translation is to specialize this runtime system itself to a particular program. And you'll get out a runtime system that is kind of just built to run a particular target program. And if you do this right, you're going to get out a program that actually navigates kind of a similar state machine just in the same way that the efficient actor program did. And if you took what I just said and you try and actually do it directly, you're going to find it doesn't quite scale. And that's because the size of the state space that you want to navigate to actually implement your actor program efficiently, the size of that scales with the number of topological orderings existing in a particular parallel computation graph. And so the number of topological orderings, of course, is exponential. And so for the simple program here, there are only two different topological orderings, so the state machine is pretty small. But if I add just a little bit of complexity to this graph, the size of state space dramatically increases, and I can't even show it all on one slide. So instead of directly representing these state spaces directly, what we do is we compile our task graph that we get from the user into a set of per-processor actors that instead are structured like interpreters. And these interpreters are configured with different dynamic state, where the state is kind of the edges that any particular actor needs to be responsible for to know that it can begin parallel work. And the idea is that these interpreters are kind of a custom runtime system specialized to the particular task-based program we want to run. And the different configurations of dynamic state that they have are going to implicitly represent the same larger state machine that we might run explicitly. And so as we send messages between each other to say that certain edges are done, we're going to implicitly navigate this sort of same state space that our efficient actor program did. And this relatively simple compilation strategy is actually going to yield quite high performance, which I'll show you next. So to do this, I'm going to talk about how we actually measure the overheads a particular parallel programming system puts upon its users. And so we're going to plot the efficiency of a system. And so what this means is this percentage is going to be 60%, means that we spend 60% of our time running application code, and the rest remaining 40% of the time actually running not application code. So we're inside our runtime system. And so we're going to kind of track for any particular task size, like how efficient can we actually be there. And we're going to track pretty much where these systems cross over this 50% line, meaning, which is kind of an arbitrary choice, but it's a cutoff point for where a system starts to spend less time doing any application work rather than doing runtime. It's going to spend more time doing runtime system work than application work. And we're going to do this by taking a fixed computation graph, kind of like looking like these stencil-like structures here. And on all the way on the left, we're going to have very big computations lasting between maybe several milliseconds. And then as I move along the x-axis, I'm going to keep the same graph, but I'm going to make these tasks smaller and smaller so that at the end, they're only running for a few microseconds. And then we're going to measure the kind of efficiency our system actually gets on these different sizes. So when I plot a particular system here, Realm, a programming system developed in our group that's task-based, on a single node of 8 GPUs, we get this curve where at large tasks, you can get quite high efficiency. But then as the task gets smaller and smaller, we spend larger and larger fraction of the total time inside our runtime system rather than actually our application. And so if I add in all the systems that we actually experiment on, you see a few trends. First, actor-based systems perform the best, kind of achieving the lowest overheads for as long as possible, where they can support computations efficiently at around 10 to 20 microseconds in this particular configuration. Then you have task-based systems, which are noticeably worse, and their performance profile is different, and they can only support computations of around 100 microseconds before overheads begin to dominate execution time. You have Ray here, which is kind of a hybrid actor task system. And Ray doesn't perform as well, but it trades some of these performance features to gain features like resiliency and elasticity, which are kind of more valuable in cloud computing contexts than these other HPC systems, which don't actually have the capability of doing this. And so many popular use cases of Ray actually have very long-running tasks where these overheads don't actually matter for performance. And so what you see in our work is that our compilation strategy can actually take our systems, Legion and Realm, that live within this task-based performance profile and move them into this actor-based performance profile, reducing the overheads they impose by around 4 to 5x. And what this means for actually real applications is that we can take end-to-end programs and dramatically improve their strong scaling. So I have two different fluid simulations here written in Legion, and I can strong scaling is I take the same problem size and I break it up on more and more processors to try and get speed up as using more processors. And so as I take the same problem and break it up on more processors, the amount of work each processor does gets smaller and smaller. So the farther that I can go and actually not be dominated by overheads is going to dramatically improve how fast I can get at these larger problem sizes. OK, so in this first part of the talk, I told you that about this, the trade-off kind of between these two program models for building high-performance parallel applications. And I showed you that we don't actually need to choose between the programmability and productivity sides of the programmability and performance of these two models, and that by using some right compilation strategies, we can actually get the best of both worlds. Yes?
So just at a high level, it seems like you take the task-based description and then partially evaluate it with respect to the runtime of the actor system?
Yeah, we kind of specialize our our task-based runtime system, which kind of can be viewed as a collection of actors, and we get out a specialized runtime system that just is only able to run the particular program we care about, which kind of cuts away a lot of the generic parts of that runtime system and gives you something much higher performance.
Is there anything important about the distributed platform that it's going to end up executing on that gets taken into account during the specialization or partial evaluation?
Yeah, so one thing I didn't particularly talk about is how we handle accelerators. And for accelerators, there's kind of even more you can do because accelerators have hardware support for synchronization. Basically, you want to really leverage that to get better performance. And so by doing the specialization further, you can kind of look into how these accelerators want to synchronize and use those hardware-supported synchronization primitives when possible, which you kind of can't do if you're looking at it a task at a time. You don't know who's going to depend on what and how this program will be configured.
So maybe digging one more level deep, and you can tell me to save it until the end. I don't want to disrupt too much. But you started by talking about this interaction between composing all these systems at all these different levels. It seems like the choices made here might impact like local kernel level optimization trade-offs as well. So is that taken into account? Have you looked at that?
Yeah, so I will say that kind of at this point of the software stack, we're kind of looking at the task-based program we gave as kind of the source of truth, where the tasks and dependencies are kind of, you can't really change them. But higher level systems, this like Leagate level programming model is the one responsible for kind of generating these tasks and dependencies. And at that level, we can do things like fusion and like make better kernels with more information. But at some point, we have to say, here are the computations I actually want to run on my machine. And just these are the dependencies required for correctness. Yeah.
You focused here on a range of task sizes, and I can see why that's very important. But it seems there's another sort of fundamental paradox here, which is we're generally taught to enable more parallelism by expressing fewer dependencies. But fewer dependencies means more messages to keep track of the possible states you're in. Is that just never an issue? Do you still want just all the parallelism you can get and let the runtime figure it out?
Yeah, so I'll say in this particular model, so I'm talking about kind of an explicitly parallel programming model. And so the dependencies here we're going to assume are the ones that are necessary for correctness, so they're precise. There's no additional dependencies here. So then any other orderings that satisfy the particular dependencies here could be exploited for performance opportunities. So then higher level systems like Legion actually are precise in the dependencies. They specify not adding any more than necessary. And so that is a property that then allows Legion to do well when compiling onto this particular system. Yeah.
So the overheads that you mentioned, it looked like it was coming maybe mainly from using a centralized scheduler for the task-based systems. Can you compare a bit, like your approach versus, say, if you built a decentralized scheduler for Legion or Realm for these systems?
Yeah, so this is a single node of 8 GPUs, so technically, I guess you could have a centralized scheduler, but I will say that the Legion runtime system itself and Realm don't have centralized schedulers. And Legion in particular distributes its dependence analysis across all of the processors, all the nodes independently. And so every node is kind of only responsible for scheduling the computations on each local node. So there's no central. In fact, I don't have these numbers, but prior work, not that I did, but from the group, evaluated some systems that have centralized schedulers. And basically, as you scale up to multiple nodes, they really have a hard time because you go to four nodes, and that's 4 times as many tasks, and the scheduler kind of can't keep up unless the schedule itself is also sharded across systems, across the nodes.
Yeah, just to clarify, if there's no centralized scheduler, then where was the overhead coming from for orchestration?
Overheads arise from all layers. Like you're going through different software layers of calling more functions. You're waiting in queues. You're using atomics to synchronize. You're taking locks. Like when you get down to running computations at the individual microsecond layer, like CUDA overhead, CUDA driver is a limitation here. So everything kind of it's like a death by 1,000 cuts when you look at reducing overheads in these systems. Yeah. Okay. Thanks for the questions. Okay. So I just discussed one component of this piece, which is about orchestrating our parallel computations efficiently across the machine. But then to achieve the best performance on a system as a whole, right, the kernels that we're actually orchestrating need to be high performance and get the best performance out of the individual accelerators. So that's what I'm going to talk about next. I'm going to talk about making certain aspects of developing these high performance kernels more productive, specifically talking about some of the recent challenges of achieving high performance on modern Tensor Core GPUs. And so this work was done in collaboration with my colleague Rupanshu Soi. So as I discussed at the beginning of the talk, each subprocessor of our modern GPU or accelerator now contains large fixed function units that take up a lot of the chip area, like the Tensor Core and the Tensor Memory Accelerator in this diagram, for performing specific computations like matrix multiply or tile data movement. And these fixed function units are then accompanied by general purpose units that perform a wider variety of computations like transcendental functions or in normal arithmetic. And so the main goal in these machines as a programmer is basically to keep this Tensor Core running at every single cycle because it contains 99.9% of the flops available on this device. So every cycle that it is not doing something is money that you're wasting. And so just to establish some terminology and context, I want to discuss a bit of the programming model of these devices. So this is like one subprocessor here, of which a modern GPU contains like 100 or so. And so I'm going to focus on just the challenges of programming one of these subprocessors efficiently. So each subprocessor is going to host some number of threads, which actually run the user programs. And the main important thing here is that the hardware is going to group these threads into groups called warps. And this has 2 main implications. So first, these warps are going to issue instructions into these functional units independently of the other warps. So one warp is going to issue a batch of instructions. Say some of them use a Tensor Core, some of them use a TMA. And the hardware will then negotiate the issued pieces. And then separate, these warps have a fixed amount of resources that they can actually access inside this register file. So if I have more warps, I might be able to get more piece chunks of this register file to use. OK, now that I told you about this hardware, let's move into some of the challenges of programming it. So as these fixed function units on the GPU get more powerful, there are two optimizations that are becoming increasingly important when programming them. The first is software pipelining, which is a scheduling optimization that reorders the execution of instructions to increase the amount of parallelism and throughput of our loops. So to talk about software pipelining, I have a little program up here, which is the core of the flash attention algorithm that's used in modern transformer workloads. So this particular kernel has three operations. It's got a gem, which runs on the tensor core, an X, which has to run on the general purpose units, and then another gem, which runs on the tensor core. So if you execute this program naively, you're going to get bubbles here, where due to the data dependencies, there's nothing else I can do, and I just have to wait until this Exp is done to start the next gem. So I'm wasting a lot of money running this program. So software pipelining is going to reorder the instructions in this loop, in particular even across iteration boundaries, where at a particular iteration, I'm going to be doing the gem from iteration I, while doing the Exp and the second gem from iteration I minus 1. And giving me some more overlap and increasing the throughput that I can get out of this particular loop. The second optimization is warp specialization, which is a spatial parallelization strategy that's going to execute different components of a GPU computation on different warps, these groups of threads. So warp specialization has two pieces. First is the strategy, which actually takes a particular program, such as this pipeline, and says which warp should actually run each instruction. And then it has an actual implementation of that strategy, which often looks like this spatial pipeline, where the warps responsible for some computation will wake up, do their computation, write it into some visible memory, and then some other warps will wake up, and then their downstream operations will run, and so on and so forth. So a key problem here with these GPUs is that the optimal strategies for software pipelining warp specialization are changing across architectures. So when the Hopper GPU came out, the community developed a wide variety of these strategies. And basically 2 years later, all those strategies were useless when the Blackwell GPU came out. And we had to develop some completely new ones to run code on the Blackwell GPU efficiently. And to give you an idea of how some of these things change, so I took that same software pipeline that works well for this particular ratio of tensor core and Exp costs, and if I just make the tensor core go twice as fast, which has been happening year over year, and then the rest of those units don't change their speed at all, which also is basically happening, this pipeline is no longer efficient, and we actually have bubbles here now, and we're no longer getting good performance. And you don't have to look at this code, but if you want to get that better performance again, you have to repipeline this loop. And many of the structure is different here, where there's more stages and the kind of dependencies inside the loop have changed. And then for warp specialization, kind of architectural configurations affect how we warp specialize. So on the Hopper GPU, simple strategies like separating data movement and compute were sufficient. But then on the Blackwell GPU, kind of very complicated strategies that break different computations across different warps and communicate in strange ways are required for good performance. And so the effects of these changing strategies can be seen when you look at the evolution of, for example, the flash attention algorithm, where we started with flash attention 2 on Ampere, and we had to wait a whole year after the Hopper GPU came out to get flash attention 3, which basically was a software pipelining and warp specialization strategy tuned for Hopper. And then we had to wait a whole another year for the flash attention 4 algorithm to come out, which proposed a completely different software pipelining warp specialization strategy tuned for Blackwell. And so there's a group of experts that are really good at doing this, but kind of the whole computing world can't wait and waste trillions of cycles training models, waiting for somebody to tell them how to use these machines efficiently. And it's a kind of bigger problem, bigger sign that our software infrastructure is falling behind the rate at which our hardware is evolving. And so I think the source of this problem is that the combination of software pipelining and warp specialization is poorly understood. Software pipelining in itself is quite well understood, actually, where automated and optimal algorithms have existed since the 90s. But when you add in warp specialization, it's an area where only heuristics are known. Kind of experts come up with strategies, and compilers are trying to apply these strategies to different pieces of code. And when you put them together, you lose a lot of this composition, where once you add in a bad warp specialization strategy, you don't even have the optimality guarantees that these algorithms provided. And so only experts today can develop and hand code these strategies, and our compilers are just can't compete. So in our work, we remedy the state of the world. And we show that we can actually derive provably optimal software pipelining warp specialization strategies and explain why these strategies are actually good. We realize this is possible by examining a variety of expert design strategies and seeing that the decisions made by each optimization don't really make sense when you view them independently. Kind of the choice of software pipelining you do is going to affect how you warp specialize and vice versa. So therefore, we model these optimizations in a joint manner, making synergistic decisions kind of between the two optimizations. And the key insight into this optimization problem is to model it as a scheduling problem, where we're trying to find the right order in which to execute instructions in our loop. But at the same time, we're going to constrain the set of valid schedules to satisfy a resource allocation problem, where we're assigning different instructions to different warps. And so finding a valid schedule is going to require us to navigate kind of how we place our different instructions on these different warps and leverage the constraints this provides. For example, that if we put too many instructions on one warp, we might actually blow its register budget and have to move things onto different warps. So we've implemented this idea in a system called Twill, which jointly discovers these software pipelining warp specialization strategies. Twill accepts a machine model that describes some features of the hardware, like how many threads it takes to run the tensor core, or how many cycles different instructions take. And then it takes in the input program that you need to optimize. So Twill operates in two steps. We're going to first use standard modular scheduling-based software pipelining algorithms to derive an initial schedule for the target loop that has the optimal throughput. And then from this initial schedule, we're going to define a series of SMT constraints that describe a joint software pipelining and warp specialization strategy for that desired throughput, and try and solve it to find a good solution. If we can't find a satisfying solution, we kind of repeat the process with a more relaxed schedule until a satisfying assignment is found. Once we do so, we're going to get a resulting pipeline program, and this pipeline has the best possible throughput that is possible under the particular GPU's architectural constraints and our model of the machine. And so our approach has successfully generated the best software pipelining warp specialization strategies for multiple generations of GPU architecture, Hopper and Blackwell, and is the first and only system that we know of that's capable of doing this. You have a question?
Yeah, how do you know it's optimal?
So by optimally here, we have a particular machine model of how fast this SM or processor can actually run instructions. And so we can prove we get optimality by saying that this is the max throughput that this particular SM could run the given computation.
So when you start with the optimal software pipelining, that's just a heuristic because you assume that's a good place to add the warp specialization strategies in.
No, it is not a heuristic. It precisely, the software pipelining, initial software pipeline states that the best that this loop could run on this hardware is like, we can clear one instruction for every 3 clock cycles. Or sorry, we can clear one iteration every 3 clock cycles. And that is just a lower bound. And so then what we're asking is, now can we find a joint schedule and warp specialization strategy that can still achieve a throughput of 1 iteration every 3 cycles?
I see. So this is like an enumerative synthesis style, where like you're saying, is there a solution that achieves the optimal software pipelining? If the answer is no, then does it achieve within one of optimal software, and then you can sort of back off. I see.
Mm-hmm. Exactly. Yeah.
Maybe, sorry to jump in, maybe I misheard. This is also saying like, just this is actually speed of light for the hardware.
Speed of light given a particular modeling of the hardware. That like, say I know that my tensor core can do a gem in 5 cycles, and I know that it takes 3 cycles to do a sign, like under modeling the hardware like this.
And, oh, I see, but you're saying you're optimal with respect to scheduling from not empirically.
Well, we also implement the schedules in real life and see good performance too.
Okay.
But it's like, it's optimal given a model that this machine can do X number of things at the same time at these rates. There's no better order.
So slightly simplified.
Yeah.
Sure.
Okay, so let's look at about how this actually works. So as we start in, we're going to take in the program we want to run. Oh, go ahead. Should I go back to the previous slide?
Yeah, I just want to run the previous slide. So, to what extent is the hardware model designed and informed by a particular program or schedule that exists for this? It seems like there's the opportunity to do so, given that it's all done in-house.
I don't think that I think the modeling is more for a particular GPU. Just the hardware offers a set of functional units, and those functional units have throughputs. And I think maybe the answer for your question is that the trend is to get better performance. We're kind of moving into worlds where these functional units are more and more predictable, where the hardware kind of, there's less variability with the software, and the hardware is like, I will do a gem at this rate for you, and I will do an exp at this for you. And so that is what, that's kind of what is being exploited here. Yeah.
Thank you.
Okay. So we take in our program, and as I said, we're going to apply off-the-shelf software pipelining algorithms to get an initial schedule. And this schedule, based on the software pipelining algorithm, says that is the best thing that we can do. So we take this and we unroll this program once. So we imagine running this program where the main loop runs exactly once, and we're going to get out a particular piece of straight line code. And from this straight line code, we're going to enumerate a set of constraints for when a particular schedule or ordering of these instructions forms a valid software pipeline. And then we're going to enumerate constraints for whether a particular warp specialization strategy or an assignment of these instructions to warps is valid given a particular GPU's architectural features. Then under the conjunction of these constraints, we're going to solve for a schedule and warp assignment strategy that achieves the minimum execution time. So let's look about what these constraints actually look like. So for software pipelining, we're going to break this down as a discrete scheduling problem, where we're trying to map individual instructions onto concrete cycle counts and resources that they need to run on. We're going to track this through a multidimensional array of Boolean variables, tracking whether for a particular instruction, the occurrence of that instruction is it scheduled at a particular clock cycle. And when we do this, then we can write down a bunch of constraints. In particular, this one is capturing data dependencies between instructions, where, for example, if I have a data dependence between this S0 and P0 operation, and I say my machine model says the gem takes 2 cycles, I cannot schedule the follow-up instruction at cycle 1 because the data would not actually be ready yet. And then for my warp specialization constraints, they're going to capture when I map these instructions onto different warps. And again, we capture these with a series of Boolean variables for whether a particular instruction should go on a particular warp. Then I can write down warp specialization constraints, of which there's many. This particular one captures the amount of data available on any warp. It's saying that the total amount of live data at all clock cycles on each warp needs to be below the architectural limit. And kind of the cool thing is that these constraints start to interact, where actually this liveness predicate is defined in terms of the scheduling predicates from the previous slide, allowing the solver to make decisions like, OK, I could run more operations in parallel and increase the register budget, or I could split them onto different warps, or I could run them not in parallel and have lower resource utilization. So once I solve these all in conjunction, I'm going to get out a schedule that tells me when I should run these instructions and a warp assignment telling me where I should run those instructions. And I put these together and re-roll this program back into a pipeline loop that has the corresponding strategy, and I can prove that it has the best throughput that you can achieve on this machine. And so we run this on some real programs, including the flash attention program, and we find exactly the same exact strategies that human experts have converged on over some time. And so these are the data flow representations of the loops that are being run. And each group of colors here is kind of the warps responsible for running the subset of these instructions. So some of these strategies are the same, where these green operations are actually data loading operations, and they're placed on the same warps across both generations of architectures. But then things quickly change, where the warps responsible for running the actual tensor core instruction has changed between generations. And then the warps responsible for doing different kinds of non-matrix multiply arithmetic has also changed between generations. And so without a system like Twill to kind of enumerate the space in a structured way and prove to you that what it gets is actually good, it'd be kind of hard to decide why one strategy is actually better than the other. Yes?
Both software pipelining and warp specialization, as I understand it, are purely in the sort of scheduling domain. And so there's no, there's no use of replacing some computations with other computations.
Yeah, there's no algebraic transformations, et cetera, like that. Yeah.
How robust is this optimization with respect to variations introduced by the system? For example, warp scheduler can sort of reorder the way in which warps are scheduled.
Yeah, so I mean, we're not modeling that kind of thing. I mean, we're mostly modeling from the speed of light throughput on the device is that it can do some number of multiplies, some number of matrix multiplies, et cetera, per cycle, and that's kind of the way we're modeling this thing. We're not modeling kind of an adversarial warp scheduler that may disrupt stuff for you. But I'll show you on the next slide that we still actually perform well despite potential variations in the hardware underneath us. Yeah.
How long does your solver to find these solutions?
Yeah. Both of these are under a minute. I think the left one was around 20 seconds, and this one was around 30 seconds.
How large is the problem? Like how many variables, how many constraints roughly?
I don't know if I can tell you off the top of my head. I mean, I think we make like thousands of variables and constraints and throw it in the solver.
And which solver are you using?
Yikes was the best solver for this. Yikes 2 performed way better than all of the other solvers. But I don't really have intuition for how good solvers run, because the same problem here could take CBC5 like 30 minutes. But Yikes, it doesn't actually mean the solver. It's like one problem is actually harder or not than the other. Yeah.
Total nitpick. Why do you have something minus itself on Blackwell? Is that just a slide?
Where you
It could
see
be zeroing it.
I see. It's just a cheaper way to zero because the size might be big.
I don't know.
I see.
It might, so the loops here could refer to dependencies across iterations. Like I might take the value in the previous iteration and subtract that to get the next one. So that's where loops can appear. Okay. All right, yeah, so then as I said, we implement these on real hardware, and show strategies generated by Twill can achieve competitive performance with those implemented by hand, like in cuDNN or Flash Engine 4, and it can perform significantly better than heuristic-based approaches like in the Triton compiler. And so in this part of the talk, I talked about some portability challenges of how to actually build high-performance software on these accelerators, especially as they change across time. Yeah.
Sorry to hold you up at all. Yeah, actually. Do you know what the peak is on these?
Yeah, so for this particular configuration, I don't want to get too far into the details, but kind of in this configuration you run the Tensor Core, the peak you can get is around 1250 or 1300 teraflops. So we're very close to peak. Yeah. Because basically what the schedule tells you is that you're running the Tensor Core at all times. And so we expect to see that in the final result. Okay. So now I show you how there are these two optimizations, warp specialization and software pipelining, that are really important for performance. And I showed how, even though their strategies are changing over time, we can use like a kind of unified constraint-based representation here in Solvit to actually get the strategies for them in a machine portable manner. And so in the context of the larger work I've done in my PhD, I've worked on these systems to build, at the top level, to build high-performance distributed libraries for end users, build distributed runtime system technologies to actually support these high-level libraries, and then build programming systems to actually develop kernels that run both across these machines as well as on individual processors. And so into the future, I think my experience working in this area has led me to believe that tackling the axes of change in our underlying hardware in our accelerated hardware is a critical problem. So our hardware is increasing in scale, as I talked about in the beginning of the talk. And it's also scaling forwards in time. Whereas we're building more complex, more powerful architectures, they're also becoming increasingly specialized and harder to program. And then there's another dimension of diversity here, where we're building, many different vendors are building similar kinds of accelerators. And then there are also accelerators kind of from academia moving into industries, such as data flow systems. And so there's a large number of combinations here of different kinds of machines that we need to support. And we need to have programming systems that actually allow us to build high-performance software on these systems. And so the large number of combinations and increasing complexity of individual components means that the complexity of programming this hardware is just rapidly increasing. And there are some domains, like machine learning, where we can pour more money into doing this to try and keep up. And already, we're still falling behind. Like I've kind of seen firsthand at companies like NVIDIA, where a new chip is released, and then armies of kernel engineers go and rewrite the software for every new generation. And there are domains that don't have as much money here, like scientific computing, where we've already just completely fallen behind. Like there are many scientific applications that haven't even been ported to GPUs, and those have been out for 15 years. And so I think this is a ripe area of research for programming systems to kind of help keep up with this burgeoning complexity. And in particular, I think there are several important problems that the programming systems community and I want to tackle in the future. So the first is around composability, which, as I discussed at the beginning of the talk. So getting composability is often at odds with getting the best performance, where, like in the sequential programming world, we have large library ecosystems we can glue together and get pretty decent performing software. But in the parallel and accelerated world, we rarely find these ecosystems, other than our initial work on the Liget ecosystem. But we need to really build composable software like this, especially for high-level users, so that we can just continue to put together efficient software rather than rebuilding everything from scratch every time we have a new application that we want to run. The second is around abstraction, where we need to continue building programming systems that abstract over these low-level, complex, machine-specific details, because even for experts, writing programs that target these machines is a challenge, and for most programmers, that's kind of impossible. And so we need to continue building these kind of systems so that we can build software quicker without actually worrying about and getting bogged down in these machine-specific details. Final challenge is around portability, where we need to build both software and compilation systems that allow us to change the minimum amount of code as we go, for example, across generations or between different vendors. We're also changing the minimum amount of code as we go from a single node system to a multi-node, multi-GPU system. And so I think there's a positive feedback loop between developments in this area. So we build more composable, more portable software. We're going to raise this level of abstraction and allow for more users to target these machines. So I have just a bit of time. I want to talk just a little bit about some concrete problems in the area of portability that I'm interested in. One about individual accelerators, where I think the programming systems we build today are really good at dealing with changes in our underlying hardware around a predefined set of axes that we kind of build that compilation system with. But then when our hardware throws a wrench in that and adds some completely new dimension we need to optimize over, such as software exposed asynchrony and modern tensor cores, our programming systems just can't keep up, and they often push a lot of the optimization burden then onto the user and are not really doing the right thing. And so there's many directions you could go here, like building compiler generators that either build entire compilers or parts of your compiler from hardware descriptions, or building portable optimization frameworks like Twill that are inherently going to be resilient to changes in the hardware. Or building more general program representations, like a project like Cypress, which I can talk about, which kind of captures things like asynchrony from the ground up. And then when you look at changes in architecture at scale, I think the lines between distributed systems programming and accelerator programming are really blurring, where complex architecture really looks like a distributed system. You have multiple dies talking over different interposers, talking about different distributed HBM stacks. This entire thing is trying to masquerade as a single processor, but it's really a distributed system. And then advancements in networking hardware are kind of pushing distributed systems programming challenges into individual kernel programming, where you have high-performance kernels now are like sending individual messages across the network while overlapping individual instructions on the GPU. And so I think there's opportunities here to build unified programming models that actually talk about a single program across across this entire stack in a single place, allowing us to optimize and perform automation across all these different layers at a time. So that'll conclude, and I told you today about my current work and future work plans, which are around building programming systems to make it easier to program these complex, high-performance machines. So that I'm happy to take questions.
So your optimization relies on the assumption that you unroll the loop once. Can you tell us a little bit more about this assumption? Is it sufficient to unroll the loop just once, or do you envision a case where you need to unroll it n times?
Yeah. So
The follow-up question is, maybe this is known, but I don't know this. Is it always the case that your optimized once unrolled loop can be rolled back, or does the optimizer make it impossible to roll it back?
Yeah, so this is actually a property of software pipelining in general that we're exploiting, where the goal of software pipelining is you construct a schedule for any one iteration, and basically you overlap this schedule on itself a few times, and there's actually a formula for how you should do this, and it produces for you a steady state that is guaranteed to be like, the majority of the time is be spent in the steady state, where every iteration after a certain point looks exactly the same. And so I can maybe go back here. Here is the steady state of the loop in the middle. And so once you run this first part, which is called the prologue, every iteration after that will execute the steady state, and it will look exactly the same every single time. So it's actually sufficient, and it's both sufficient and precise, I forgot the other word, to actually unroll this exactly once, because once you have, if you execute this whole piece of code once, you've captured both the priming of the pipeline, the steady state of the pipeline, and the draining of the pipeline. So it is both sound and precise to do unrolling once. And so because of that, we can actually always re-roll it back, because we know how to compute this steady state from a particular schedule of an individual iteration. Yeah.
You were talking about sort of orthogonal or out-of-the-blue challenges, and also are working in the context of distributed. I'm curious about, as I understand it, right, most of these things are done in fairly reliable environments. So what happens if you have high rates of message corruption, drop, duplication, failure, reordering, nodes going down? Is that a future we should be interested in, and what are how would that fit into your vision?
I personally have not worked that much in this area of resiliency and elasticity. I understand that, especially as we scale up, and you just have enough processors, the math of the probability of any one of them failing at any point is increases at certain scale. So I think it is a reality for people who are really doing large scale training, and for them, I think there is work in there to do. I think that it's unclear kind of what trade-offs you want to make. For example, is it worth being resilient to certain kinds of failure if it means the rest of your program goes much slower? Is checkpointing just sufficient in that case? Or is there, because in our experience, I think when you try and add features like elasticity and resiliency to a particular programming model, it does come with significant costs, even in the case where nothing is failing. So I think there's trade-offs to make there. And I think you really want to be specific for your application and really know about the failure rates you have for a particular model before you maybe go commit to implementing such a thing in your programming system. Because in general, I think the approaches can be too slow. Maybe with application knowledge, you might be able to do much better than in a generic system. Yeah.
So you mentioned there being sort of a lagging gap between what our hardware looks like and kind of the programming systems we have to support implementing efficient programs on that hardware. Do you view this particular solution for co-optimizing kind of software pipeline and warp scheduling, do you view it almost as like a Band-Aid that like with our current programming model, here's how we get the best solution, such that we need a better programming model? Or do you think this is kind of like a general technique we can apply in the future?
So I view it more in the latter, where I think it's like ideally, I didn't show the full program, but you can imagine that there's like, say, a Triton program that implements flash attention. In an ideal portable world, that same program just works across each generation of architecture. And right now it doesn't, because the compiler is not smart enough to lower that program the right way on each new generation hardware. And a system like Tool is like one of the pieces that such a compiler might need in order to continue delivering the best performance with every new generation. And I particularly really like tile-based programming models. I think that they're a really good abstraction for how people should think about these architectures. And I think that one area of research is just can we make these models actually continue to perform well on the accelerators we build? Because right now they're actually not. It's a lot of work every time a new model comes out to make that compiler port well.
People developing these architectures, right? Like, have really good intuition that this will speed up computations, and yet it's taking a year to schedule them well, before your work, right? Like, did they just make them too complicated? Is it only when you get to the distributed, they're good at their job, right? They didn't just throw some more ALUs on and figure we'll get some performance, or they didn't just grow the tensor, or did they? Right? Like, I mean, there's something that they did to make this problem maybe harder than I feel it should be.
Well, so I would say that, I can't actually speak to concretely what the hardware designers are doing, because I don't know what they're doing. But I will say, like, maybe from like mathematical modeling of the machine, you think that this would be sufficient, but I think the general trend though is that problems like this were usually actually handled by the hardware. Like on older generation GPUs, you didn't have to do this because kind of maybe the latency difference between the gem and everything else was large enough that this didn't matter. Or maybe that because because these instructions on older generations were fine enough granularity. For example, every instruction was only doing a 4x4 matrix multiply. And so it was actually fine to just interleave those instructions with everything else within an individual loop. Your compiler like MBCC or PTX could just do that for you. And so it was kind of automatic to programmers. But the trend now is just that these matrix multiplies are giant. They're like 256 by 256. And the semantics of these instructions are then also complex to the compilers, where it's not just for a concrete example, old TensorFlow instructions were all in the registers. So kind of standard LLVM style analysis was enough to do all the optimizations you want. But these instructions, like for example, they're reading and writing arbitrary pieces of specialized memory. They have side effects. They require multiple threads to coordinate to use. And so the normal compilation techniques don't do as much for you. So then more and more burden goes on the software to like figure out how to use these instructions in the right way. So that's kind of a general trend. I think the architects are aware of this, but they're like, software will adapt at the cost of not putting as much on the chip and putting more ALUs for the Tensor Core to use. Yeah.
I'm trying to sort of unify this with the actor-based model as well. If you had some sort of like communication within this loop, or maybe outside the loop, but either way, do you think that such a technique like Twill could also co-optimize for network throughput and utilization high?
So definitely. I think that the framework itself is kind of very abstract, and like we don't care what the instruction actually does. We just need to know how long it takes. The main difficulty with doing something like this is that we need to have static information about how long these instructions take. And then when you start talking about networks, especially networks that are switched and there's congestion over them, it becomes much harder to predict how long these things take. And kind of solver-based approaches to scheduling, especially that uses kind of discretization of time, it's hard to deal with kind of variable latencies and things like this. But that's something we're actually looking at currently. But you can imagine that if you could actually bound the amount of time in some way that these networked operations take, you could totally find a schedule that overlaps them with other compute on the device, which is kind of what the kind of kernels people write today anyway. Yeah, go ahead.
Sort of a follow-up on that is like, then, it becomes sort of the other piece of it is then if you have like one sender, one receiver, you could co-optimize those schedules as well. But then you have to optimize two potentially separate kernels is just kind of the problem of heterogeneous compute in general, I guess. And do you have any ideas for how to make that scale and compose, or is that something that kind of has to be done at different abstraction layers?
Yeah. So I don't know about that particular problem, but I will say that this issue of, how much of the program do you want to see at once to optimize is something that we have looked at in prior work. And, for example, this actor task thing, we actually have to very carefully pick how we shard up these graphs across multiple nodes to make sure, what you don't want and what doesn't work is one node actually describes the amount of work that 128 nodes are going to do. And that is something suddenly your program runs out of memory or you spend ages compiling this particular thing. So I think at some point, there's a trade-off between the more you can see, generally the better you can do, but then you have to pay for it in the amount of time you spend doing the optimization. And I think you have to cut off somewhere where you're it's not worth the amount of gains I'm getting from this are not worth it anymore because I'm going to spend too long having to think about it. And so I don't know where that trade-off is. For maybe some systems it's worth it. You're going to run the code enough that it's worth it to spend all the time doing it, but then other systems it's not.
Okay, cool. Yeah, let's thank.
Thank you, everyone. Thank you for the questions.